Hi, I'm Jeremy Lee. I'm the lead applications engineer for B&R in the Southeast region, and to me, automation is my specialty.
All right, welcome to today's episode of This is Automation. Today we have a special guest, Jeremy Lee. Thanks for joining us, Jeremy.
Thanks for having me.
Of course. So could you just take a quick minute and tell us a little bit about yourself and your history at B&R?
Yep. So I've worked at B&R for about 9 years now, just kind of programming machines. My educational background is I have a degree in mathematics and electrical engineering, and about 2 years ago started in the online master's program in computer science at Georgia Tech, where I'm specializing in machine learning, and I suppose that's what qualifies me to be talking with you here on this topic today.
That's right. So, spoiler alert, we are talking about machine learning today. So, Jeremy, could you just tell us a little bit more about that program and kind of what was your first exposure to machine learning, and why is that something that's interesting to you?
Right. So, my first exposure really was let's say in an educational context, was the Intro to Machine Learning course in the program. That's taught by two professors, Charles Isbell, who's now the dean of the computer science school at Georgia Tech, and Michael Littman, Brown University, who has a big name in machine learning. And the topic is just cool, I suppose. I mean, it's certainly become kind of a pop culture reference almost in the way it's kind of permeating our lives. And wanted to understand that. My first exposure in real life, it's probably hard to know when exactly we start to get recommendations for things. Netflix and Google, they're learning about us and trying to predict the things that we would like to see. So it's kind of permeating our lives whether we know it or not.
So yeah, I guess as far as how most people have probably seen machine learning for the first time, it's probably in some of these highly publicized applications of machine learning, like IBM Deep Blue, which famously defeated one of the chess champions, Garry Kasparov, he actually lost the first game and then ended up winning the match, but then they rematched, and Deep Blue ended up winning. Another system that people have probably heard of is IBM Watson, which, famously bested Ken Jennings and Brad Rutter in Jeopardy. So those two guys, Ken Jennings was the longest win streak at 74 wins, and then Brad Rutter was the largest prize pot. So Watson was able to beat both of them, right? And I think there's a little bit of a common misconception about how that happened. So Watson has no real. It's not like Watson is doing Google searches in the background, right?
No. It really is taking a combination of systems that are embedded in machine learning, so natural language processing, to even get the speech, the text as it's read out to Watson, get it into some form that it can do some work on it and understand that question. It's natural language processing. Then it has to go out. It has to generate some guesses and then kind of score them about how well it thinks it fits to the answer, and then it chooses the answer from there. So yeah, that's a very complicated system. One thing that's kind of interesting that we love to see these machine learning agents or artificial intelligence agents play games for some reason. Right. I think they're great test beds. Yeah. Games are very complicated. They're repeatable in some sense. But the promise from Watson was that it could then be deployed to certain real life things like cancer diagnosis and treatment, for example. And it's kind of a cautionary tale in that it turns out when it was deployed in that environment, it did okay. There was always, some oncologist sitting over the top, watching what Watson did, and it was graded out to be just okay. I don't know where it stands now. I don't know that they kind of gave up on that job, but the initial reviews were kind of tepid.
Right.
Yep.
Yeah, and that is where we see a lot of new machine learning algorithms and such being tested, is in the world of games. You have, well-defined theories behind the games and controlled variables and controlled environments.
Yep.
So it's a good test bed for these. A couple more that, those were IBM's projects. Google DeepMind has obviously done tons of these. So AlphaGo, maybe the most famous of those, arguably. So this was back in 2015. They beat the 3-time world champion.
Right.
And then again in 2016, about a year later, after some modifications, they beat probably like arguably the best Go player in the world, 18-time world champion. And then, they've kind of iterated on those kind of projects where now with more complicated games like StarCraft, where you have a limited exposure to the environment, where there's this like fog of war,
right,
and you gain more knowledge as you go. This, was as recently as the beginning of this year in January 2019, where Alpha Stars, the name of the project, went 10-1 against 2 of the top professionals in StarCraft. And again, people are like, well, it's a computer, of course it's going to win, right? It's faster, it can do more clicks and more things like that. But actually, they like artificially limited the reaction time of Alpha Star to be slower than the pros, and similarly limited the APM, actions per minute, in StarCraft. So the numbers I have, it's Alpha Star was 277 actions per minute, which is a lot, right? But if you look at the number that the pros put out, it's 559 in those games. So even being handicapped a little bit, Alpha Star was able to kind of top these 2 professionals in StarCraft. So those are implementations of machine learning in games, right? Which is, again, pretty common, but there's some practical applications out there already, right? So we're seeing it in self-driving cars, right?
Yes.
I think Tesla is very famously engaged in this, and there's plenty of other cruise automation that are, using machine learning to implement self-driving cars, autonomous cars. There's natural language processing. You see that in your phones, right? Speech recognition, same kind of thing. Computer vision. You already mentioned medical outcomes analysis, where you can take, a scan of a human body, apply an algorithm, and say, all right, there's a 85% chance this person has, X type of cancer or something like that. And that's, getting more and more popular. And of course, we're seeing some in the finance industry as well, right? Where trading algorithms and things like that, how is the stock market going to perform tomorrow? Should we make this trade or that trade? These are all kind of practical implementations of machine learning, right?
Yep.
So we've talked a little bit about where it's being used now, and both the kind of like academic research side with the games, and then also the practical side, which kind of shot off that short list. But can you just tell me what is machine learning to someone who doesn't know what machine learning is?
Right. So if we think about traditional computer programming, we're sort of programming against a set of rules, if condition, then some action or outcome. But in machine learning, we're not explicitly programming the rules. We're instead going to allow some algorithm and model to apply the rules for us. So we'll simply parameterize the model and let it process the data as is, make some adjustments. That's the learning part of it. It will say, make a prediction or guess. The model will say, no, that's incorrect. It'll adjust the model and then guess again. So it's programming without using explicit instructions.
And there's different types of machine learning, of course. So what are some of those?
That's right. So the 3 main categories are supervised learning. So this is where we're going to make some prediction. And that prediction is made using data that's already labeled. So I should say rather it's trained using data that's already labeled.
Right.
So we'll maybe dive into that in more detail in a minute. But then the next category is unsupervised learning. So this is a class of models and algorithms where we don't have labeled data. We have some data with some features, things that describe the data, but we don't know what it is. And instead, we're going to try to glean some information out of that data, just how similar are the items, say, for example. There's also, in the realm of unsupervised learning, this idea of dimensionality reduction, or maybe another way to put it is, given the features, the elements that describe the data, which ones are important and which ones aren't. And then the third major classification is reinforcement learning. So this is a subcategory where we want to train, let's say, learner to find optimal policies given an environment, so that the policy is the set of actions that should be taken given the state of the environment, and those actions maximize the reward, say, of the agent.
Maybe we can just run through each of those kind of in more detail. So starting with supervised learning. If I understand the way you explained it, we have a set of data that has labels.
Right.
So we're training a model based on that given set of data.
Yep.
And then we're providing it novel information, and it's making predictions based on that training.
Yeah, that's right. So maybe to have a more concrete example, let's say our data contains information about cats and dogs. So the label is whether that information, that row in the database, is describing a cat or a dog. And then the columns in the database are the features of the animal, in this case, the weight, the height, the length, the color, et cetera, et cetera, et cetera. So the supervised learning models then look at the features, make some guess about whether it's a cat or a dog those features are describing, and then learns to kind of do that given the data. So that's the training process.
Right.
Features in, labels out, correcting until it's able to make a pretty good guess about what it was. Then in deployment, we are taking unlabeled data now. We want to make predictions about things we have not seen yet, cats or dogs we haven't yet labeled. And hopefully the model properly trained is able to do that with some high accuracy.
So correct me if I'm wrong, what you're talking about is discrete labels?
That's right.
So this would be kind of like a classification problem is what we call this in the machine learning world?
Yeah, so there are kind of two flavors of the supervised learning, say, models. There's classification, so I have some discrete labels, cat or dog.
Healthy or unhealthy.
Yeah, exactly. Cancer
whatever.
or not cancer, right?
Exactly.
To use the medical analysis. There's the other family where we're trying to guess numbers. We're trying to predict the temperature for the day, things like that, and that's called regression.
Okay.
So we're talking about classification and regression in the context of supervised learning.
Okay. So with regression, would it be fair to call those continuous labels?
Yes.
As far as like analogous to the discrete labels of classification?
That's right.
Okay.
Yeah.
And then could you just give an example of like a little more in depth of like what classification is, like how you would do it? Like there's certain methods or? Sure.
So we're dealing with a family of models or algorithms. So just to list off a few, one is k-nearest neighbors. And I think as you start to learn about machine learning and some of the models are highly mathematical type of deals. Others are kind of, in a way, meant to mimic the way we think about problems as humans. So k-nearest neighbors, you can imagine if you plot out your data points on a graph, then you want to make a guess about a new label. So you've got your dots on the graph, and then you plop a new dot down. In k-nearest neighbors, we're simply going to say that new dot is going to be the match its nearest neighbors. So if I have my cats and dogs, you can imagine them laid out in a graph, and I throw a dot down. If I had 5 nearest neighbors, so the K is the number of nearest neighbors I'm going to look at, throw my dot on the graph. 3 of its nearest neighbors are dogs, 2 are cats, then I'm going to say it's a dog.
It's a dog.
That's all it is. So that's k-nearest neighbors. Another form is a decision tree. So you can imagine I have a tree and I throw all my data into the tree, and at each node I make a decision about what to do with that data. I want to split it into different paths in the tree, and I will pick out one feature that describes the animal here, cats and dogs in this case, and split based on that feature. So if the animal is above 5 pounds, I'm going to say I'm just going to split to the left. It's below, I'm going to split to the right. And keep doing that until I eventually come to the point where I have only either all cats or all dogs, and then I'll label them as such. That's decision tree. The model that's most popular in popular culture is neural network. So that's the one that people seem to get the most excited about.
Yeah.
It's sort of hard to describe in a podcast, but neural networks are meant in a way to mimic the way our neurons function. So I'm going to take each feature about the cat and dog. I'm going to kind of pass it into a node and multiply it by a weight. And if that excitation, the way the brain works, that excitation reaches some threshold, I'm going to kind of turn on that neuron. And that ultimately results in some prediction at the end to try to oversimplify it maybe. Final class of classification algorithms is a support vector machine. So again, imagine you throw out all your dots on a graph. I'm trying to pick a line that I can draw between all the points that puts the largest gap between the points, if you will. So the likelihood that data actually belongs on the left side of the line, cats, or the right side of the line, dogs, is maximized as the largest gap. Yeah, so that's a quick and dirty rundown of some supervised learning algorithms.
Yeah, and I'm sure we could do a full episode on probably each one of those, right?
Right.
So can you talk about loss functions and kind of like what does that mean and what are they used for?
Yep. So these models need some way to gauge how well they're doing. So I'm making predictions. How good are my predictions? So the loss function is just a measure of that. So I know the true label, and then I might say take the absolute difference between the two, and that's my cost function, my loss function. So if I guessed it was a cat and it was a dog, I penalize myself 1 point, right? And then I add those up over time, and the lower the number, the better. And that's the simplest loss function. There's any number of these, but as I kind of set out to define how well my algorithm's doing, I need some loss function to do that.
So the loss function isn't necessarily used to change the model. The model isn't changing itself with the loss function. It's more just a gauge of how the model is performing.
Yeah, it depends on the model. So the way neural networks are trained, it has a feedback loop. Okay. So the loss function is used to determine how to update the weights of the network. Okay. Decision tree doesn't have a feedback loop. It just simply processes the data, spits out a guess, and then tells the programmer, the model maker, how well it did. So it depends on the model.
Okay. And then I guess similarly with regression problems, what are the common types of those?
So the family of models we talked about before are also have analogous implementations for regression. They're called the same thing. It's just that the implementation and the loss function might be different depending on what you're using. So for k-nearest neighbors, let's not say we're talking cats and dogs. Let's say we're guessing home prices. So I might do the same deal. I'm going to throw down homes onto a graph and then plop a new one down. The price of the home, I'm not going to say that it exactly matches its 3 nearest neighbors. I want to make, some average maybe between the 3 in this case. So same deal, just a different kind of outlook on how you're using the end result.
Okay, good. So just to summarize supervised learning, we have discrete labels, cat or dog. These fall into the classification type of problem. And we have continuous labels like numbers, stock price, home price, the examples that you were giving. These fall into the regression problems. They both kind of share similar algorithms that are just implemented maybe slightly differently, different loss functions. And then, just in general, we're providing some set of training data to the model. These are historical observations that have been labeled by presumably a person in most cases. And then given new data, we're making a prediction.
That's right. Yeah, the whole idea is making guesses when it comes to supervised learning. Okay. Exactly.
Good. And then are there any sort of challenges or issues that are common in supervised learning that people should look out for?
Right. So it's in many sense kind of all about the data. So the models are only going to be as good as the data that they're trained on. So this is a whole different class of problems, right? Where did the data come from? If it was entered by a human, there's human error to account for. So the idea of data cleaning and data wrangling, even collecting the data, I mean, that's why we have this kind of somewhat new job title, data scientists, right? I mean, their job is training models, but also and gleaning information out of those models, but also just the collection and the sanitation of data to begin with. So there's that data problem. A second problem in data is the number of features. So I think this is probably especially true in automation, but people just start collecting data. They throw sensors out on a machine and collect data. And the more features that you have, the harder it is to train the model, the more data that you need in order to properly train it. You're, in some sense, training the model on features that don't matter, maybe. Right. And so that's a problem. Now in the learning of the model, there's this problem of overfitting. So I can parameterize my model. So with k nearest neighbors, for example, the parameter I have to change is the k, the number of neighbors I'm looking for. And if I want that model to overfit, I would select k of 1.
Right.
Now, if I pass my training data back into the model to see how well it performs even on the data it's trained on, it will get every guess right. It'll plot that dot right on top of the dot it was trained to be. And that is the classical example of overfitting. So
the problem there being that when you use data that's not from your training set, then it can just be wildly, inaccurate.
Right. Yeah. The model's no good.
Right.
And so the problem of overfitting is one that machine learning people have to be very concerned with. Yep. So we want our models to be able to generalize. Having the goal is not necessarily to have a model that gets every single guess right. It needs to be able to adapt in some sense.
Moving on to unsupervised learning, can you give us a quick intro to what that is and how it's different from supervised?
Right. So the names there are somewhat misleading, supervised and unsupervised. I mean, in neither setting there's a human being necessarily looking over. There's a family of algorithms where there's like a man in the middle who gets to have some say in what's happening. But in general, it's neither is supervised or unsupervised. The idea in unsupervised learning is that I still have some data, but I don't have labels, or maybe I don't care about the labels in a given setting. What I want to know is perhaps how similar are they? So they're to put some algorithms to it. There's algorithms like k-means. So I am saying, similar kind of to k nearest neighbors, I'm saying that there are certain averages that exist in this world of data, 2 or 3 or 4 of them. I want this model to go out and find them and then assign the data to that average point. So here I'm just, in a way, saying how similar are rows in the database, but not explicitly saying I believe they're cats and dogs.
Right.
Yep. That's unsupervised learning in a nutshell. Unlabeled data, but I'm trying to glean some information out of it.
So do you have like an example of when you would use unsupervised versus supervised?
Yeah. Right. So the obvious case is where I don't have the label.
Sure.
So again, I'm doing some data collection or have done some data collection, but I haven't taken the step of labeling it. This is one way to generate a label, even if you don't, maybe there's this kind of term domain knowledge, maybe by domain knowledge, I know that there are 4, products that fit this data set. There are millions of them and I can't go in as a human being and label each one. So I'll have an algorithm to try to do that.
Okay.
That one is the one that I think makes the most sense. This is also a way of, there's this process called feature engineering. I want to generate more features about my data set, and the cluster assignment in say k-means is one way to do that. I can add an additional column to my data set by running a k-means algorithm on it.
So the good use cases for unsupervised learning are we don't have labels for our data,
right.
Or we're trying to find labels for our data. Basically, if you don't have a good clean training set that's labeled.
That's right.
You would kind of turn towards unsupervised learning. And then we're just giving it this training set of data that is unlabeled and is finding the relationships between those different data points. Is that fair?
Yeah, you got it. Okay. Another use for unsupervised learning is when I want to remove columns from my data set. That's called dimensionality reduction. There's this term, I think we kind of touched on it, the curse of dimensionality. The more features I have, the more data I need to properly model it. So algorithms like principal component analysis are going to go and say which features explain the most variance in this case. I actually want features that have variance. So you can imagine if I had a column in my data set where each entry was the same number as 0 variance, is of no use to me. I can't glean any information out of it. So principal component analysis helps explain which features explain the most variance, and then I'll choose to use only those features, some number of them when I go to train my supervised learning model, for example. So the two can go hand in hand.
Yeah, so that's a really interesting one where like I guess in like your cats and dogs example, like if one of your features was like has hair, then that would be responsible for exactly 0 variance in the data set.
Right. And principal component analysis is going to go out and kind of rank the features in terms of how important they are, if you will. And hair would be at the very bottom. It has no value.
Yep. So that's unsupervised learning and supervised learning.
Right.
The two that we've covered. And the third one that you mentioned was reinforcement.
That's right. So this is kind of the family of algorithms that are concerned with finding optimal policies. So the setting here, I have some world, and that world is defined by states and actions that the agent can take in that state. So you can imagine a mouse in a maze. I can go forwards, backs, left, and right. Those are my available actions. And then the state is, where I am in the maze. So the policy then that I'm trying to teach this agent is the one that maximizes the reward. So, what's the reward? The mouse is trying to get to the cheese. And I generate some reward function. Getting to the cheese is 100 points, if you will. And then I might also shape my reward function so that I penalize just randomly moving around. So every single move that doesn't result in getting the cheese gives me a -1, but ultimately that drives me towards finding the cheese. So reinforcement learning is, again, the collection of algorithms that help me find that policy that maximizes the reward.
Okay. So where would you see this being used?
So we've already talked about some of them, right? The machine learning algorithms that are teaching machines to play games, those are typically using reinforcement learning, maybe in combination with some of the other stuff we've talked about, but those are reinforcement learning problems. I think we'll talk about some in the realm of industrial automation that could make some sense, but really any place we have some state, set of actions and some reward function to maximize is a candidate for supervised learning.
Right.
Self-driving cars. I think another example, my policy, I want to maximize my reward that's getting to the destination, and I want to do it in the shortest amount of time possible with the fewest number of collisions and mistakes made.
Yeah, and so this is, I think, an interesting point where this is being used in a lot of those applications of machine learning in games, right? With, AlphaGo and AlphaStar. If we can define these real-world problems as games, where they have a reward function and we're defining the environment and the actions that you can take, it basically is a game, right? And so then we can use these same principles and kind of translate them to solve real problems.
Yep, that's the dream. I think that there's a lot of research going into that area. You don't think I know that there's a lot of research going into that area. It turns out that some environments are well suited to this and some are not. So even in the context of games, there's a company, OpenAI, I think that's Elon Musk's group, but they've put out an environment, OpenAI Gym, and it's got, I think, every Atari game that was ever made, and it's simplified things in such a way that it provides you the state and the actions, and then you build up a model to find the policy to play that games, and it's good at half of them and bad at half of them.
Yeah.
So on average, it's like okay.
Right.
So there's again some domain knowledge, perhaps, which environments make sense to be approached in this way, which ones don't. But this is where the research is right now. Can we just throw environments at a model and it spits out the best thing to do, and then we're all out of jobs, right?
Yeah, so I think I've seen that there's like an infographic that shows like all those games, and it's like relative to like where 100% is like human performance levels, and some of them are like really bad, like Centipede or something
really
like that.
Interesting.
It's really bad, which is you wouldn't think that, but and then it's really good at sound like 300 times better.
It's interesting. You would think that why what what makes any Atari game really that much different from the other, but it is the case. It cannot play sums, it can very well play others.
So maybe jumping ahead here, but in the context of something like that, like how do you make that decision of whether it makes sense to use machine learning in an application, and how do you define the success of that? And like because like inherent in machine learning, right, we don't really know 100% what's happening all the time.
Sure. I mean, that's not to go on a tangent, but this is black box to a lot of people. I mean, even not to get maybe political, but people feel like they're being mistreated maybe in some way. They had all this data collected about them at some point, and now they're like powerless against it. They are creatures of their habits and they can't help it. Now they're being recommended these things to do, but not to go down that path. To actually answer your question, how do we know what to use, when to use it? So there is I don't know if you call it a theorem, but a mindset, this idea that there's no free lunch, so the no free lunch theorem. So given a problem, you're not guaranteed that this thing will always work. So what I mean to say is you can't always use a neural network to address every problem. They are ill-suited to certain problems that maybe decision trees are better suited to. So that's the idea within just say supervised learning is selecting an algorithm to address a certain problem. Now, whether the problem can even be approached given what you know about it and the models you have available, there's some just try it idea. I mean, it's costs you not much given the platforms that are out there to try a neural network approach to supervised learning, a decision tree approach, and then you just look at the loss function, right? Which one scores the best on that problem? So then the final way is that just that domain knowledge, we know from experience that certain approaches will be successful here in some law.
So that's reinforcement learning, basically kind of trial and error done by the agent to get the most reward.
Yeah,
right,
that's really it. It's it's pretty amazing because as I understand it's the way that AlphaGo is done, and in any reinforcement learning program, really you're not really programming the rules.
Right.
You provide the legal actions that can be taken in a given state, but you don't really necessarily even say what the goal of the game is. You just have a reward function. Now that information is kind of buried in the reward function, if you will. You get the cheese. The goal of the game is to get the cheese, but you just kind of throw it in there, tell it what it can do, and it finds out the best way to do it. It's really pretty neat.
Yeah, I saw a really interesting one, I think just yesterday actually, where kind of similar. The goal was, like progress as far as possible. And it was just like a human form. Basically, it's given certain actions so you can move all your joints. And these things basically like learn to walk. And there's some like idiosyncratic movements where they're like waving their arms while they walk for some reason. But yeah, it's really interesting. They can like jump across gaps and things like that. Man. Pretty cool.
Yeah. Yep. I've seen a video of a guy training a model to play Mario, right? And it's very, 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 very good at it, but it doesn't know it's playing Mario. Right? Yeah,
exactly. Yeah. I think that's another interesting thing where some of this like artificial intelligence stuff starts to creep in, where it's like when a model like generates some like novel way to do something, it's like, is that intelligent? I don't know. So like I know in the AlphaStar example, right? Like the players are like, this did some really creative thing. This like strategy that it implemented is intelligent.
Right. Yeah. There's another model out there that plays Dota, this game Dota, that's I think again coming out of Elon Musk's group, and same thing, it's professionals watching this saying, wow, that's actually advanced strategy, and it feels like learning, right? But I don't know, very impressive.
I don't want to get into too much detail, but like other terms that people may hear when they're talking about machine learning or artificial intelligence, could you just give us like, quick top 5 things, other things we should know besides unsupervised, supervised, and reinforcement learning?
So I think the term you hear the most is deep learning. People are, ooh, deep learning.
Yeah.
That sounds deep. And really all deep learning is the family of algorithms concerned with neural networks, but in particular large neural networks. We have lots and lots of neurons arranged in many layers. But for the audience, there's really still just neural networks applied in specific ways.
So neural networks will be a good one to know about.
Yes.
Presumably anybody listening would be able to have a conversation about machine learning.
Yeah, they're ready to go.
That's all you need to know. So I guess on that note, what would you need if you wanted to get started with machine learning, whether you're an OEM machine builder or just someone who's interested in it? Where do you start with this kind of stuff?
Yeah. So the Python programming language is I would say the popular one right now. And to that end, there are Python deployments, in particular one called Anaconda that you can go and download, and it will install all of the packages that you really need to get started. So NumPy makes has a collection of libraries that implement MATLAB sort of functionality, and so it's a big number crunching library. And then Anaconda comes equipped with scikit-learn, so that has all of the algorithms that we've talked a bit about today and many more, actually. It has example data sets, so that the sort of hello world programming examples, the IRIS data set, anyone who's looked into this, seen the IRIS and the numbers data set. So IRIS is a collection of data that describes irises, and models can make guesses about which type of iris they are. And the number data set is a collection of pictures of numbers, so you can actually do some vision type applications that people have actually hand-drawn numbers, and then it will look at them and guess what number it is with very high accuracy. So all you really need to get started is to go download Anaconda and pull up an example on the internet and get going.
Yeah, and so I guess once you move from that to a real application, the biggest problem is finding good data.
That's right.
Right?
Yep. So, if you want something more meaningful to practice on, there are data sets out there. I don't have any to list right off the top of my head. I mean, I know the government has public data sets that you can go and play around in. There is a website that you can go to and actually participate in competitions. So they'll provide a data set. And sometimes it's real life customers saying, hey, here's our data.
Right.
Help us do something with it, make predictions or what have you. And so you can do it in the context of competitions, and you can also find examples there where from past competitions, people have published their approaches. So you can get your hands on some data. Then ultimately, if we're talking in the context of, your profession, then you need to kind of make it your job to go out and get it, save it away, and then do something with it.
So any tips on how to get good data?
So
hard question.
Yeah, it kind of is a hard question. So, I mean, you need let's say context of industrial automation, you need some way of collecting that information. So sensors on the machine, accelerometers, things like that, some way to store it. So this is typically going to be some database that with the advent of cloud technology, you typically have easy access to. Your platform needs to support the ability to get that data there, but otherwise save it away. And you need lots of it, right? So make sure the data is collected in a clean way. You don't like to see empty entries in a given column or row. That kind of poisons your data set. The data has to be cleaned or removed entirely, but otherwise just have lots of it and start to try to do things with it.
As far as using machine learning in the industrial automation space, where are some places that either you've seen it or you think would be good applications? Yep.
So I've definitely seen machine vision. I think that's the big one, and that's very important to us in industrial automation. So you can imagine product coming down a conveyor belt, and I want to determine what it is so that I can make some downstream decision about it, or maybe I'm doing inspection. Is the product properly assembled or not? And on and on and on. So, of course, machine vision has been in machines for some time, but they're using, let's say, classical ways of doing this. So it's just edge detection algorithms. Things are tuned maybe to pick up on certain things. That tuning process is timely and hard. You have to kind of be a specialist. Whereas with machine vision and machine learning, we are just going to take example pictures of these things, pass them through some model, and then it will make some guess about it. So they're very advanced algorithms for kind of decomposing images and determining, if they contain certain things, what of them, how many, where are they located within the picture, things like that. So I think machine vision is, I think, one big obvious one that is already in deployment today. Another is preventive maintenance. So again, where we've discussed algorithms that make predictions about things. So I can perhaps make a prediction about how far am I from needing to have some maintenance, or I am detecting certain maintenance conditions here, given the state of the machine, the inputs that I'm seeing. So condition monitoring and preventive maintenance are certainly going to be, and already are, examples in use where people are saving time and money on machines by preventing mass failures with some preventive maintenance.
Right. Do you think that we'll start seeing maybe more or less data centric and more like physical implementations of machine learning where, for example, in robotics, if we're teaching robots moves or letting the robot optimize a process, some sort of reinforcement learning.
So right, again, reinforcement learning is just the holy grail. We'd like to just throw a robot into an environment and
let it figure
provide
out
it some reward function for picking up. You picked it up 100 points and take the next action. I understand that this is being done to some extent. I personally think it's a difficult class of problems.
Sure.
I think as you kind of look at the implementation, the use of machine learning in industrial automation, a lot of times the original approach to solving the problem is suitable. It's in something that doesn't make sense to train the robot to do it. But for very complicated things, or maybe to take maybe a different example, tuning control loops or parameterizing systems, especially if they're extremely complicated, is one space where this could be very useful. I mean, we are able to simulate things to a great extent, so we can throw this reinforcement learner in there just like we're trying to learn to play Atari games, with the goal of it being to find the parameters, the policy, the parameters that generate the greatest reward, the least amount of whatever overshoot in a temperature system, say, for example. So there I think are very real use cases for reinforcement learning in tuning control loops, potentially in teaching robots to do things. And it certainly, I think, could be done. I think it probably has been done. I worry a little bit about the difficulty of those problems where we have I don't know how many companies, just whole companies, are trying to do the automated cars, right? So I mean, this is a complicated problem, but so is teaching a robot to do something. So I think it's going to be difficult, but we'll see.
Yeah, I think that the point you bring up about reinforcement learning, though, is a good maybe implementation of simulation.
Yes.
It's a good reason at least to start looking at things like simulation and digital twin and data collection, getting connected to the cloud with your machines and with your manufacturing facility to enable this kind of thing in the future.
Yeah, absolutely. You should be forward thinking. And I think there are examples where it's maybe not reasonable or certainly undesirable to do these tuning operations on site. You can imagine some of the material you're working with is extremely expensive, maybe caustic or dangerous. You don't want to be maybe around it, exposed to it.
Right.
So you have to observe from a distance.
Yep.
Anyway.
And it's slow, right?
That's right. Yeah. And we're talking about temperature systems. It take hours, maybe, I don't know, even days for certain things to come to stability. And the more you're able to simulate, the better. That's true in industrial automation in general, but in the context of machine learning, it gives you another way to approach the problem.
All right. Any closing thoughts on machine learning?
I think that we'll see more and more of it. It's already being deployed and saving companies a lot of money. I think the one area we've not talked about is process optimization. What I mean is just supply chain, the best way to lay things out, the amount of material you need coming in a given day so that you don't have to warehouse things, say, for example. Those are real life examples where machine learning is being deployed and saving companies a lot of time and money.
All right, Jeremy. Well, I appreciate the discussion. Really enjoyed it. Thanks so much.
Thanks for having me.
All right. So in future episodes, we're going to be diving into even more exciting topics. I'm sure we'll have some more stuff on machine learning. There's lots more to talk about. We'll talk about IIoT and cloud, which are a few things that we mentioned in this episode. We'll, of course, cover the traditional automation technologies as well, servo motors, when to use a PC, when to use a PLC, all those kind of topics. We've got more special guests lined up and more special topics that you definitely want to keep an eye out for. So make sure you subscribe to the podcast on Apple Podcasts, Spotify, or wherever you listen to your podcasts. And if you enjoyed it, please let us know by leaving a review on Apple Podcasts or a comment if you're so kind. And if you'd like to get in touch with me or have a question or idea for the show, just pass that along to me on LinkedIn or by email at automationpodcast@gmail.com. Thanks again for listening, and we'll see you next time on This is Automation.